Welcome back to my channel, Predicting the Future. Today, we'll talk about simple linear models. And specifically, we're going to talk about the simplest model of linear models, which is a one predictor variable, which means we only have one x in a linear model. So, although it's the simplest, but it's the basic foundation for all the complex models in linear models, and some of the non-linear regression models. So this is really important foundation of all the topics in regression. So let's begin. Suppose we have a bunch of data x, a pair of data xi and yi from observed values, and we want to feed this data in terms of a linear function. So we define a random variable here. We define the capital Yi as a linear function of a constant shift on y, which is b0 plus b1xi plus an error term, which is epsilon I. All epsilon I are, we assume they are independent, identical, normal random variable with mean 0 and variance sigma squared. Xi are non-predictor variables, we call them predictor variables, Xi, and Yi we call them response variables. And an alternative model for the Yi can be written as another form, but they are basically the same linear functions. It's just sometimes one way of writing the same model is much simpler when we're doing analysis, and then the other one. So the other way is we can write as the y as a b0 star, same constant, different constant, and b1 times bracket of xi minus x bar. So this is another way of writing the same linear model, which we will see later. So the first thing we want to do is we want to find the best fit of this model. So the most obvious way of doing that is using maximum likelihood estimators. So we first define the likelihood function of this linear model, which is basically, because yi they are all independent, different. They are all independent, so we can write this the PDF of yi as a product of those PDF of yi's. Then we use the maximum likelihood function to find the maximum estimates of the b0 and b1s, and eventually, it's actually equivalent to. You see here, it's actually equivalent to minimizing a quadratic form, which is the least square. So basically, the maximum likelihood estimations for b0 and b1 is the same as least square estimations. So let's find the estimations of those parameters. So we take the derivative on the log function here with respect to b0, b1, and sigma square. We get the estimation of b1 as a linear function of yi, while ki is a function of x values. So xi minus x bar divided by sum of the x squares, area squares. And b0 is estimation of y bar minus b1 hat x bar. Same of those b0 star and sigma square. Sigma square hat. Sigma square hat is actually one of the important estimations, and it's actually a sum square divided by n. A sum square is the observed value of yi minus the fitted value of yi and squared, and summed all the yi's over all the sample yi's. So the sigma square here is the maximum likelihood estimation of the sigma square is SST divided by n. And ki is we just mentioned it's a linear function. It's a function of xi, and there's some property of this ki. Sum of ki is 0. Sum of ki times xi is 1, and sum of ki squared is 1 over sum of SSE of xi. So yi is the estimation of y is the statistical estimation of the y value when we estimate the b0 b1 with its own point estimations. So what we see here, that one of the very important thing about SSE is that SSE is the sum of the EI squares. So EI hat is the error term of yi minus the fitted value, the point estimate of yi, and SSE is the sum of those yi minus yi hat square. And we can see that we can prove that we can actually show that the expected value of b1 hat and b0 hat is unbiased estimator of its own parameter b1 and b0. Another thing we're going to talk about is a theorem about b0 hat star, which is b0 hat star is what? B0 hat star here is actually b0 hat plus b1 hat x bar. This is the alternative model, the parameter of b0 of the alternative model of this the first model we just mentioned. So we can prove that the b0 hat star and b1 hat is actually a bivariate normal random variable, follows their unbiased estimators of its own parameter b0 hat star and b1, and also these two are actually independent because we can prove that their covariance is actually 0. So let's prove that. It's very easy to see. So first we check it. It's a covariance is 0. So the covariance of b0 hat star and b1 hat is we plug in its estimators, and all we have to do is to take out the constant and write the y bar as the sum of yi's as the sum of so there's some errors here, yi where the yj where the j is now equal to I plus yi and the covariance with yi. It's actually because y and yj they're independent when I is now equal to j, so it's actually becomes just one term is sigma square, so that becomes 1 over n sigma square times sum of ki, and because sum of ki is 0, so the whole thing is 0. Same thing, we can prove that the b0 hat star is the unbiased estimators b0 hat sigma square b, and the variance of b0 hat star is sigma square divided by n. And b1 hat, we can also find b1 hat is also unbiased estimator. We can also find the variance of b1 here. We won't go to the details of the calculations. And because of the independence of b0 hat star and b1 hat, we can actually find the variance of b0 hat. We can't find that earlier easily because b0, we know the b0 hat is actually a linear function of b0 hat star minus x bar x1 hat. And now we know that b0 hat star is independent of b1 hat. Then when we find the variance, we can just write it as the sum of its own variance, and now we can find the variance of b0 hat star. So now the next thing we want to do is that we want to find out some very interesting things about, for example, the variance of the point estimate of sigma square hat. Also, we're going to introduce mean square errors, which is unbiased estimator of sigma square. And we'll see that the sigma square hat is actually not unbiased, it's a biased estimator, but it's a consistent estimator of sigma square. But unbiased is always, in most cases, always better. So we see here that we're going to soon prove that the mean square error is actually a better estimator of sigma squared. So let's go through. Let's look at a decomposition of the SS. A decomposition of the yi minus the linear part of the estimation, which is b0 star minus b1 times xi minus x bar, and that becomes only the error term. So that the sum of the actual error terms square. We can rewrite this term by introducing the b0 by introducing the point estimators of b0 hat star and b1 hat. Rearrange these terms, we can actually find we can find that it's actually a sum of these three terms. The three terms here is actually quadratic forms. So if we write the first term here as q, second term as q1, third term as q2, and last term as q3, we can see that q so q1 let's see why this is a quadratic form. We introduce the quadratic. What is quadratic form? We introduce a theorem called quadratic form theorem in the previous videos. So if you can always pause the video and go back and check that video, because you're gonna need some of those the theorems there. So let's see q1, q2, q3. So those q terms are actually a quadratic form of the zi, which is yi minus b0 star minus b1 bracket xi minus x bar. And because q1 we can show it, but because it's going to take a long time, so I'm going to skip that. You can try to find it yourself on the paper. Not that hard to find it. So q1 is actually one quadratic form. It's a square of the z bar, the mean z squared. And q2 is actually this form, which is actually also a quadratic form of zi's. It's a square of the sum of ki and zi's. q3 is also a quadratic form as well. So q1, q2, q3, and q, they're all quadratic forms. Then what we can find from so we can find that one interesting is a q3 divided by, well, at q3 here. What is q3 is actually this SSE. Q3 is n times the point estimate of the sigma squared, which actually SSE, sum of the yi minus the point estimators of yi squared. So q3, so we can actually prove that q3 divided by the sigma squared is actually chi-squared n minus 2 degree of freedom. Let's prove this theorem. So let's first look at the q term. Q term is actually when yi minus its mean, it becomes normal with zero mean. So when we divide by the standard deviation, it becomes a standard normal. And we know that when we square the standard normal, it becomes a chi-square of 1 degree of freedom. And because they're all independent, the sum of those terms becomes a chi-square of n degree of freedom. So q divided by the sigma squared is a chi-square with n degree of freedom. And we have also proved in previous theorem is that b0 star hat, b hat 0 star, is a normal distribution with mean b0 star and standard and variance of sigma squared divided by n. So if we minus the mean divided by the standard deviation, it becomes a standard normal. Square it becomes a chi-square of 1 degree of freedom. Same for the q3 term, q2 term. Q2 term is also normal divided by minus its mean divided by standard deviation becomes a standard normal, and square it becomes a chi-square of 1 degree of freedom. Now what we left is q3, and by the quadratic function we introduced in the previous video, we know that q3 divides chi-square is q3. Now we can conclude that q3 divided by sigma squared is a chi-square of n minus 2 degree of freedom. Because q term is n degree, this Q1 divided by sigma square is 1 degree, Q2 divided by sigma square is 1 degree, so it becomes n minus 1 becomes n minus 2 degree of freedom. Now we can go further and look at the expected value of sigma squared, the point estimate of the variance. So this is take out the constant term. That will become the expected value of the sum of square errors, SSE, and eventually we can get that is the mean of the sigma square head is actually n minus 2 divided by n times sigma square. It's not actually sigma square, but it's a little bit shifted sigma square. So this is this is a biased estimation, but when n is large, this will converge in probability to sigma square. So this is a consistent estimator of sigma square. So this is the error here. This should be biased estimator. So now let's look at bias as not always good. So let's see if we can find biased estimator of sigma square. So we can see here if we reverse the n and n minus 2, and we take the expected value of this one, the sigma square. So if we times the sigma square head with n divided by n minus 2, then this is called mean square error. So if we look at if we plug in the sigma square head into here, which is actually mean square error is actually the SSE, sum of square errors, divided by its degree of freedom, which is n minus 2. We just proved that. So MSE is called mean square error. Why it's mean? Because it's a sum of some values and divided by, we call it the total number of quantities, right? So that in here that will be the total, the number of the degree of freedom. So this is called mean square error. And mean square error is actually unbiased estimator of sigma square. And the variance of sigma square and mean square errors can also be found easily. Okay, so now mean square error is good. We found estimation of B0, B star, and those things, and variance and estimation, the point estimations for sigma square as well, using mean square error. Now we want to find further influence on this model. The first thing we want to see is what's the confidence intervals for those parameters. So let's find the confidence intervals of B1. If divide B1 head by because B1 head is unbiased estimate of B1, we divide by its mean B1 divided by its standard deviation. We're expecting to have some good statistics, right? But we don't know the variance. We don't know the variance of V1 because we don't know the sigma square, which is unknown parameter. So we're gonna replace that unknown parameter with its unbiased estimate, which is MSE, mean square error. And we can actually see that if we divide we can actually construct a t-distribution as follows, as what I showed in here. So divide by its sample variance, a standard sample variance, but both numerator and denominator we're gonna also divide by its actual variance. Then these two will cancel out actually. So let's look at the sample variance of B1 hat and the actual variance of B1 hat. And it's actually when we simplify that, it's actually a chi-square of n minus 2 divided by n minus 2 squared. And so that becomes so B1 hat minus B1 divided by standard deviation becomes a t-distribution. The numerator part becomes a standard normal distribution, and denominator part becomes square of chi-square divided by its degree of freedom. So that's exactly the definition of of t distribution, and based on this statistics, we can find the confidence intervals of our B1 parameter. And same for B0, it's the same, pretty much the same calculation. So it's also a t distribution with n-2 degree of freedom, and that's the confidence interval for B0 as B0. And now let's find more interesting stuff here. We want to find, the next thing we want to find is the confidence interval of the mean, the expected value of YH, where for any YH. So we're trying to find a confidence interval for the mean of YH. Remember, it's not at YH itself, but the mean value of YH. So let's see how we can find that. So we know YH hat is a point estimator of the mean of YH. So YH hat is the expected value of YH hat is actually expected value of YH. So, but what about the variance of our point estimators, YH hat? YH hat, the variance of YH hat is actually this one. It's here we're using the series we just proved in the previous, just the one we just proved. So we use the B0 hat star and B1 hat is independent. We find we find the variance of both, plus them together, and that becomes the variance of our point estimator YH hat. And we replace the sigma square, which is unknown, with the mean square estimator. We get this the sample variance of the YH hat. Now, same as the previous ones, it's actually it actually also comes down to a t distribution with a -2 degree of freedom, or because of the mean square error here. So we can find a confidence interval for the mean value of YH as this one. So this is the confidence interval, 1 minus alpha confidence interval. And next, we can also find the confidence interval of a new observation. Let's say we want to predict some value of a new value, not from the sample, but new value. So that becomes a prediction of what the value will be in. We want to find a confidence interval of this new value, new observation. Let's say YH, when X is equal to XH. And the way we find it here is we also try to find a statistic follows a certain distribution, and then try to find the confidence intervals there. Same here. So let's see the error term here, which is E hat H, which is YH minus is point estimator YH hat. And it's easily provable. It's the expected value of VH hat is 0. And now, because YH is a new observation, so it's independent from all the X1, so it's independent from YH hat, it's independent from Y1, Y2, Yn, so it's independent from the point estimator YH hat. So we know that YH and YH hat are two independent random variables. So now we can find the variance easily without worrying about the covariance. So the variance of VH hat is actually the variance of YH plus the variance of YH hat, which eventually becomes this term here. And same here, we don't know the variance, the sigma square variance, so we replace that with the point the unbiased estimator, mean square error, MSE. It becomes sample variance. Now, if you divide by the EH hat, which has mean 0, divide by its sample standard sample variance, it's actually a t-distribution with n-2 degree of freedom. Now we can find the confidence intervals of new observation YH, which will be this interval. So then next thing is what we can find is another inference we can find a confidence interval for m new observations, the sample mean of the m new observation. Let's say we have m new observations from YH1 to YHM, and we want to find a confidence interval of y bar h, which is this one. We want to find the confidence interval of this one. So YHI are independent from each other. They're also independent from the YH hat, which is a statistic from Y1 to YN. So if we define RH hat, which is YH hat minus YH bar, and then RH hat is a normal interval with mean and variance as follows. We can prove the mean of of RH hat is 0, because we can also find the variance of that, same of previous ones. We can also estimate the variance with the MSC, become the sample variance. Therefore, we can also very similarly, we can find that this is actually RH divided by standard sample variance of RH hat. It's actually a t-distribution with n-2 degree of freedom. So now we can find the confidence intervals for YH bar of m samples as this. So this is the new confidence interval for that. The next thing is that let's say we want to find a confidence interval for not only one observation. We want to find, let's say, a confidence interval for several observations, new observation, prediction. We want to predict a couple more than one observations. Then we can't use the previous one we want to predict the mean value of several observations, several different prediction XH. Then in this way, we can't use the previous one, which is only for, we can't use this interval here because it's only for one XH. Now we have multiple. We can't just have multiple of all the let's say XH1, XH2, and say that those intervals for each combined has a confidence interval of 95%, because if they're independent, when they multiply those probability 95%, that's definitely less than 95%. And we want specifically a confidence interval that's greater than, equal or greater than 95%. So this is now gonna work, and it actually a method called walking hoteling confidence interval for the regression confidence band for a regression line. So that means that it's a regression for the mean of the regression line, the regression line itself, no matter what XH is. So that's, you can have multiple XH, and you can predict that confidence intervals for all those multiple XH responses with working hotel confidence interval. I won't go into details, but that will be introduced with the W term, which the W squared is actually 2 times the F distribution with 2 and n-2 degree of freedom. So next thing we want to talk about is we want to make some hypothesis testings. We want to make decisions. We want to see, the thing we want to talk about here is about whether the slope is 0, or there is a slope or there's no slope. So basically x is correlated with y, or it doesn't correlate with y. So our hypothesis is h0 is b1 is 0, which means there's no correlation, versus h alpha, which is b1 is not equal to 0. There is a correlation. We want to test that. And the first thing we're gonna do here is to do another quadratic form decomposition. So we're gonna decompose yn minus y bar squared sum of those same terms, and it can be proved that this sum of terms we call sum of SSTO it's actually equal to sum of the fitting value minus the mean of y squared plus the sum of yn minus plus the SSE term. I won't go to the details, but the intermediate terms is actually 0. So this is a decomposition, but this is not we can, if h1 is true, we can use the quadratic form theorem. But if h0 is true, which means the b1 is 0, then which means the yi, they have the same mean. All the yi have the same mean, which is b0. So that SSTO is because the sample variance, right, of the yi term, and the last term SSE, no matter whether b1 is 0 or b1 is not 0, the last term is always has a chi-square distribution, which is just proved in the previous theorems. So now we know that under the null hypothesis, remember, under the null hypothesis, SSTO divided by sigma square is actually chi-square with n-1 degree of freedom. SSE divided by chi-square, which is means chi-square, which is actually chi-square with n-2 degree of freedom. Now we can use the quadratic form theorem. We know that SSI divided by sigma square is chi-square with 1 degree of freedom. So why we care about SSI? We're gonna see soon. Besides being able to decompose SSTO into sum of squares of SSR and SSE, we want to also associate a concept called degree of freedom to those sum of squares, regardless of whether we are under null or alternative hypothesis. So we want to associate the degree n-1 degree of freedom with SSTO, and 1 degree of freedom associated with SSR, and n-2 is always with SSE. So now we can see it's very similar to under the null hypothesis. Those terms are all correct. When not under the hypothesis, the degree of freedom is not the same of chi-square distribution. So, but we also want to associate those degree of freedoms here, and we're gonna use that later. Now, once we associate the degree of freedoms, we can define two more terms. We define the MSR, mean square of regression. That will be SSR divided by its own degree of freedom, which is 1, and MSTO, which is SSTO divided by its degree of freedom, which is n-1 here. So the expected value of MSR. Let's look at the expected value of MSR. MSR, if we simplify that, it becomes actually a b1 hat squared times sum of xi minus x bar squared. Now, if we use the equation in 3.6, which is the variance 3.6 here, which is the variance of b1 hat, that will be sigma squared divided by the sum of xi minus x bar squared. We're gonna use that here. So let's come back to where we are here. Let's find the expected value of MSR. So MSR is actually expected value of b1 hat squared times the sum of xi minus x bar squared. But expected value of b1 hat squared is it's actually variance plus the mean squared, right? So that's and times that one. But the variance of b1 hat, that would be the 3.6 equation. That would be the variance sigma squared divided by sum of xi minus x bar squared plus the mean of b1 hat is actually b1, that becomes b1 hat and b1 squared. And that gives us the mean value of mean MSR. I see here, if b1 is now 0, then the expected value of mean MSR is definitely greater than sigma squared. And that gives us an idea of testing. So we see that expected value of MSR is always greater than or equal to the expected value of MSE. So if H alpha, the alternative hypothesis, is true, then MSR divided by MSE should be greater than 1, right? And if H0 is true, then MSR divided by MSE should be close to 1. So now something we can use. So that inspires us our test statistics for testing H0 where B1 is 0 versus B1 now equal to 0. Now we can define that statistic as a F statistic. So under null hypothesis, we know the MSR divided by chi-square divided by sigma square is a chi-square distribution. MSE divided by sigma square is a chi-square distribution as well. Now with two chi-square distribution, when they divide, it becomes F distribution. So under null hypothesis, the F distribution here, F, the sigma square terms are cancelled. Now it becomes F distribution with this is the one F distribution. It becomes F distribution 1 degree of freedom and n minus 2 degree of freedom. So we can conclude that by using the F distribution here, we can conclude that F star, if less than with the type 1 error equals to alpha, then when F star is less than F, and the value when the value at F distribution when the probability is 1 minus alpha 1 and minus 2. When it's less than that, we can conclude that H of we can conclude that B1 equals 0. Otherwise, we can conclude that the alternative hypothesis is correct. Now, let's first look at F star. It's actually you can see the F star is actually a square of T distribution. Why? Let's expand F star. F star is SR minus 1 MSC divided by SSC divided by n minus 2. So that when we simplify, when we rearrange a little bit, that will actually becomes B1 hat divided by the standard deviation of B1 hat squared. But B1 hat under the null hypothesis, B1 hat, the mean of B1 hat is 0, so that becomes a T distribution here. So that becomes a square of the distribution. So the equivalent test of F distribution is actually a T distribution, but here the T distribution is a two-sided test. We take the absolute value and compare to the T value compared to the confidence interval boundaries of the T statistic. So now this two is the same. So, and I think that's it. That's all I want to talk about here today for one predictor variables. We talk about, let's just go with a brief. We tried, first we found the estimators and then we find the relationships of those parameters, and we can actually find bias estimators for all the parameters b0, b1, and the sigma square, and also its variance. And then what we did is we tried to find the confidence intervals of those parameters and estimations. And then the last thing we talk about is hypothesis testing of whether x and y are correlated. And that's it. Hope you like it, everyone. Thank you.